So, welcome back. Go ahead and ignore this. Today, I wanted to finish up the all pair or the shortest, or the closest pair of points problems. I did want to note that over the last day or so, I did a full write-up and pushed it out to the lecture notes that are for this course. I did a full treatment of everything that we've covered so far, full text and everything like that. And I also added, these visualizations that I've drawn on the on my tablet instead. This is the usual treatment here, where you've got these two slices, this left and right slice, and those are the maximum number of 6 points right there. That for any point x, y on the left partition, you only have to look at that region in the right partition within that right slice, right? And at most, there are at most 6 points there. Yeah, go ahead.
Is our point on the partition or infinitesimally close to the partition?
It doesn't really matter, because you can always just go epsilon over, right?
All right.
It can be on the partition if you want to, but then anything with an equal x value, make sure that you prefer to put it over on the left partition, right? Now, the actual points that we give you are randomly generated, so the probability that you have the same x coordinate is extremely low on any of those. I also went through and did the analysis that this is the naive by doing it naively like this for each point in the left partition in the left slice. If you do pairwise it up with the point in the right slice, you're going to end up having order n squared behavior. But after limiting this using the geometry, then you only need to look at that points within that region. Okay. I then went on and talked about implementation details, including the full pseudo code here. Again, this is pseudo code, not necessarily real code here. But I did add all of the implementation tips and tricks and details that you would need to actually implement this. In particular, how do you get this slice, right? The presentation up here was assuming that you can get these two slices, right? So first of all, you've got m, right? Because if you sort everything with respect to x, first of all, then to split it up into the left and right partitions, that's all you have to do is go to the middle element, right? If there are 50 points, then put 25 over here, 25 over here, and because they're already sorted with respect to x. Okay? Now, how do you get those two slices? Right? Well, once you've got delta, right, all you have to do is scan over delta in your left partition, scan over right delta in your right partition, and that's your slice right there. Right? Now, the trick here is, how do you get the slice with respect to the y variable, right? Now, if you build this left slice and you build this right slice, the trick is resort it, right? You can resort it with respect to the y-axis. And if you do that, then you can use binary search to find, I guess if you do that, then of course you can just go, if you've got your y, you can go up delta, you can go down delta, right? So you don't need to do too much work if you've actually sorted with respect to y. Now the catch there is that you are resorting that every single time, which leads to order n log n in the non-recursive part. Right? And let me go ahead and jump to that here. Where is it? Where did I put it? Right? Yeah, here. So you're going to have these, at most 6 points that you have to look at over here, but you're also going to have to sort all those points in the right slice. And when you do that, there are at most n divided by 2 points over there. And so any n log n sorting algorithm is going to be n divided by 2 log n. And now the master theorem no longer applies, right? At least the way that the master theorem is usually presented. Don't worry. There's an actual fourth case, or a generalization of the master theorem, and I didn't put that in the write-up here at all. But basically it says that if you've got a logarithmic factor over here, that's okay. It bumps it up by a log squared. n log n versus n log squared n. The only difference there is a logarithmic factor. Is it going to matter in practice? No, log is so small, who cares? Right? So, but I did put in that detail there. All right. Now, and then I went on to argue here that it's actually not 6 points, that it's actually you can get it down to 5 really easy just using geometry, and then you can get it down to 3 using advanced geometry. But I didn't go that far. Basically, there's your equilateral triangles, right? You can see the points 1, 2, 3 on the line, 1, 2 over here. Those will all fit in a semicircle, but they're all on the border of the semicircle. So to actually, restrict the points further, you have to move these 3 equilateral triangles one way or another, necessarily pushing 2 of those points out. So it's actually only 3 technically. I talk about why they do that in the text here. Basically, the original paper from 1976, I went back all the way to the original paper in 1976, and the original paper presented it like this, and everybody just copies it. But also, the original paper did it like this because they used the Manhattan distance. Remember the Manhattan distance? You go down the street and then over because you can't walk through buildings. And so it's going to be the sum of differences of absolute values of coordinates. Right? 3 blocks down, 2 blocks over, instead of whatever that is with Pythagoras' theorem. Right? Okay? So implementation details all over the place there. What I wanted to do is I wanted to make your lives a little bit easier by continuing with this exercise. That using binary search, if I gave you an array, say like this array here, right? I want to call binary search on this range here so that if I, for example, 2.5 and 8.5, if I called binary search on that, what should it return? What I want is everything from here all the way up to here. In other words, I want you to give me the indices of all those things. The index here is 9. And then the index here going 1 extra would be 15. Why 1 extra? Because, well, we want to use it in expressions like this, right? It'll go 1 extra over there, right? Before we continue to develop this, let's go ahead and think about some other cases here. This should return, let me go ahead and put this into a comment here. This should return 9 and 15 because we have to understand what we want here, basically. So what if I have binary search of, say, I don't know, 1 and up to and including 8? What should that return? What would our expectation here be? 0. All right, 0. Why 0? Because I want this first one. I don't want this last one. I don't want this middle one. I want all of the ones. So that should be 0. And then what about the right index? What should that return?
Is it inclusive?
It's within the range here. So inclusive, exclusive, because we want to use it in expressions like this. If I gave you j, I would expect to go to j minus 1. Right?
Okay, so it's exclusive?
It's inclusive, exclusive, yeah. So I would want to include 8, but then I would want the index to be 1 beyond that. So what index is this?
We already did it. It's 15.
Oh, 15, thank you. Excellent, I don't have to.
What about like the 8.5, you're going 1 over?
Well, yeah, but that would be like right here.
That's so that you actually get the 8.
You want the 8.
Okay.
If there were an 8.5 in here, then 8.5, then I would want to include that. It's inclusive on both endpoints of lower and upper, but the indices are exclusive. So maybe I'll put that in as a clarification. Lie within the range, inclusive on both ends, but the second index is exclusive. All right, there we go. Okay. What about some other special cases here? What if I wanted, say, just 1 through 1? What would we expect there then? Certainly 0 because we want to include it. And 0, 1, 2, 3, 4, 5, 6, 7. Okay. But one more would be 8. There we go. Binary search range. What if I did something completely outside of what's in this array? Say -10 through -5. What would you expect then? Right? It's nothing. So how do we get nothing out of this? Nothing to the left, I should say. Will that do it? Careful. The second index is exclusive. What if I did this in array, so I want everything from 0 to 0? What will that give me? I don't know if that will even be an error in Python, but it'd give me an empty array, right? It should. I don't know what it does. What? No.
None to none will, but I don't think 0 to 0 will.
No. Oh, yeah, 0 to 0 is going to give you an empty list. It should. That's my expectation. Right? What about the other end? What if I went from, say, 10 to 50? I guess you could still do 0, 0, but it'll be on the other end now. However many, what was this, 15, 16, 17, 18, 19, and 19? I would expect that, right? That kind of behavior. And maybe I should be documenting this all up as examples in my documentation here. But are we good on that so far? Can we just start?
Why don't you make it for something that doesn't exist, though? Like
Well, why wouldn't you?
index doesn't exist.
Why wouldn't you?
Oh, well, I guess it is.
I mean, if you knew that it didn't exist, why are you calling this function to begin with? You know it doesn't exist. Don't call the function.
That's
Right? This function is telling you it doesn't exist by giving you those indices.
Yeah, but I guess if that function didn't exist, why write that line of code anyway?
Okay. Are we good on the behavior that we
Yeah,
want?
sure.
Okay. So
Sorry.
this is going to be a modified binary search. So let's start with an actual binary search because it probably will be helpful to use that as a subroutine for this thing over here. Okay? Let me make sure that we are, yeah, there we go. All right, we are online. I think everybody's here, but later on, if you want to look at the recording, I just wanted to make sure that it was actually working. Let's go ahead and go with just a regular old binary search that takes an array and a key. And this one is just a regular old binary search. Returns on index at which it takes, let's say, this method takes, I keep calling them arrays, but Python doesn't like to call them arrays. What are they? They're lists. So it takes a list of elements assumed to be sorted in ascending order, and a key, and searches the list for the key. Right? Returns an index at which it finds an element matching the key. Now, keep in mind that we're going to be writing these for just regular old integers. If you want to use this and adapt it for your closest pair to find those slices, both vertical and horizontal slices, you're going to have to be careful because, well, of course, you know, you're going to have x, y coordinates instead. You'll have to adapt this or generalize it in some way. Okay. So it returns unindexed. Why do I emphasize un? How does binary search work? Remember? What if there are lots of ones? Is it guaranteed to return the first one or the last one? It could return any one of them. It depends on how it splits the array or the list, right? At which it finds the matching key. Now here's another difference, right? What if it doesn't? What if that element is not in there? For example, in the runs that we had here, 2.5. That would end up returning none traditionally, or -1 for an unsuccessful search. We don't want it to do that. We want it to return 9, because That's the cutoff. That's where it would be if it existed. Lots of languages, their binary search implementation actually do this for you. For example, Java. In Java, if you use binary search, it will return something negative on an unsuccessful search, but the magnitude of that negative value, if you add n to it, tells you the index at which it would be if it had existed. Right? So this is a very common behavior. So let's go ahead and implement that. Right? Returns an index at which it finds a matching element. If no such element exists, returns the index at which it would be found if it existed. Now, why is that useful? Well, if you've got this element in here, is it already in there? No. But if you were to put it in there, it would be at index 5, right? Okay, well, I want to add it, and I want to maintain the ordering, so put it in at index 5. You see how that would work, and that would be useful? Right? All right, so let's write this thing. Traditional binary search, of course, right? What I'm going to do is I'm going to set my n here. N is equal to the length of the array, right? You can make some quick checks here immediately. For example, if the value, the key, is less than the first element, then what should I return? Should I return -1? It belongs at index -1? Nope. So you want to you want to search for -10 here. Where would it be if -10 were in this? At 0. So let's return 0. Else if, and remember Python does not have else, it has elif. Yeah, go ahead.
Well, wait, if we return 0, wouldn't that say that it is at the first element of the list?
So you do have to disambiguate that. You would have to say, does it contain it, and is its index 0? So, or here, if it's in there, it would be at index 0. Go and check at index 0. Is that what's there, right? That's common in a lot of programming languages because it's giving you more information, and if you need to, you can check for yourself to disambiguate that by calling contains or was successful search or something like that. It's difficult to do that, to design a function that does that, because a function can only generally return one thing. In Python, we could return a tuple that is a true false for the first one. Yes, it exists. No, it does not exist. And then an index. And then you would interpret the true and false as yes, it is there. It's in the list, and it can be found at this index. No, it's not in there, but you could, if you wanted to, insert it at this index. It's just one way, 6 of one, half a dozen of another, right? Okay. All right, so else if, I'm going to check the other way too. If the key is greater than a race of n minus 1, right, key, then what should I return? N minus 1? Remember, we're going one more, right? So we should return n. In fact, that makes sense, especially in this case, because if I wanted to find, say, 1,000 in this, would it be inserted at this index right here, at the last index? If it did, then it would look like this, 1,000 and then n. And is that sorted? Nope. So if you were to insert it at a particular index, what index would it be at? At the end, which would be n. Right? Okay. And I'm going, by the way, again, I'm going through this exercise because it might help you on your points exercise, but also because this is divide and conquer, right? Yeah, go ahead.
Would you have to use the index n minus 1, or could you just use the -1 in this case? Or?
For Python, yes, I think you could do this. I think it looks icky, but that's just me. I think, and also, I don't remember. I'm 99% sure, but me crossing my fingers and then going and having to read a bunch of documentation to make sure it's just quicker to just do this, right? All right. I'm going to start my left and my right indices. My left is going to be 0, and my right is going to be n minus 1. Right? And you can do this more Pythonic how? with a compound assignment like this? Yeah, that works. In fact, that's what I mean by Pythonic, right? If a Python person were looking at two lines like that, they would say right next to each other saying, those are just assignments. Why didn't you do that in one line? They'd get all pissy about they'd get all pissy about it because you're not doing it the Pythonic way, right? So I'll do it the Pythonic way, right? All right. So while, and that's not Pythonic either, right? While L is less than or equal to R. So a Pythoner would yell at me and tell me to do what? Don't put those parentheses there. That's not the Pythonic way. Right? Yes, you can put them there. They will be ignored, but it's not necessary, so do it the Pythonic way. Right? All right, what now? I need to look at the middle index between L and R. Right? L and R are starting at 0 and n minus 1. I need to jump to the middle index to see is that so that I can see is that the thing I'm looking for, or do I need to then recurse? And we won't be doing recursion here. This is just the straight up iterative version. Will we look at the left partition or the right partition? Right? So I need my m here. How do I compute m? On a number line, if you've got a number here and a number here, how do you get the number in the middle?
You take the average.
Average. So L plus R divided by 2. Nope. And careful, yeah, you want to floor this. Or in Python, an even better way of doing this is integer truncation, explicit integer truncation. How do you do that? Double slash. Right. There we go. Yeah.
Is that always going to be the same as like the floor function, like the?
I believe so. In fact, I think in Python, math.floor is guaranteed to return an integer as well. So I think, don't quote me on that again.
Well,
I don't know,
what if
but
it's a negative number or something?
it'll return a negative. This will return a negative too, right? If L plus R happens to be negative divided by 2, it's still going to be negative.
Oh, yeah.
Right.
Never mind.
But hopefully you're not doing that because that's out of bounds of indices, right? So if that's what I'm looking for, the key, right, then I'll return m. Otherwise, if what I'm looking for is less than the mth value, do something else, and else if. I always have to remind myself. I write correct code and then I have to go back and make it Pythonic. Yes, that is a dig at Python. Else, something, right? So if it is, this is, by the way, an else if the array of m is less than the key, but of course you don't need to write that explicitly. Why? Because that's the only other possibility, right? It's either equal, greater than, or less than, so else. Right? So this means that I need to search in the left half. Right? How do I update my L and my R, so that I'm searching in the left half? Do I update my L? Nope. I update my R to be m minus 1. Why?
Because you've always
I already looked at m, the mth value.
done is a piece of garbage.
L, I update that to be m plus 1. Right? Now, you do have to be careful here, because what if you don't find it? L and R are getting closer and closer and closer until they're equal, in which case you still look at that. L plus R divided by 2 gives you L, right? And you need to look at that, and is that the thing I'm looking for? Yes or no. In either case, the next iteration, if it's no, then they'll go past each other, and you break out of this while loop. At which point, that is an unsuccessful search. So what do we return? Normally, if I were to present this in, say, a Computer Science 2 course, I would say none. But remember that if no such element exists, we're redesigning this function to be more useful. It returns the index at which it would be found if it existed. So L and R have passed here. Where would it exist if it were there?
Lower
Oh, it
was
would
lower.
exist at the
it would exist in the lower one, right? That's where you would put it because this needs to be shoved over to make accommodations for it.
But would L be like, would L only be decreased by 1 or R would only be increased by 1 once?
Well, they're only off by 1. This is L, and then R is equal to L plus 1 because they've passed, right? And so it would be L. Right? Through experimentation, you can find, or you can write it down on a piece of paper to be absolutely sure, or you can just go through experimentation and find out.
Well,
Right.
would that something if it's less than that, or, if it's less than the key, then you would return L. Is there any situation in which you would want to return R?
No,
Oh,
because then you would be putting it
above.
to the above what you just told me was less than the other one, right?
Okay.
And then that would be out of order.
Yeah, that's a problem.
That actually makes our lives a lot easier now to write this one. How does that help us?
Oh,
I don't even know if I need this. Yeah, I'll use it. So I'm going to set the size of the array here. Call that binary search on the array and the lower. Right? What's that going to do? That's going to either return the index at which you found one of them, or it's going to return the index at which it would exist if it were there, right? So be careful. What if it returns this guy right here? I searched for 1. Oh, I found it. It's right here. Is that what I want? I want to move it over here. I want to move it over here. I want to move it over here. I want to move it over here until either I've fallen off the edge, or in the case of 9 here, if it gave me 9 here, then I would want move it, move it, move it, stop right there to get that last 9. That is a simple while loop. So while you've not fallen off the edge, and the thing to your right is equal to the lower key that you've been searching for, I minus minus. Can you do that in Python? No, and I have no idea why. Don't ask me. Right? All right, same thing works for the other way. J is equal to bin search, or binary search, sorry. The array with the upper as the key. Oh, there we go. And what we need to do is we need to make sure that we move that way to get everything that might be equal. So, and make sure that you don't fall off the edge too much. So while j is less than n, and the array of j is equal to the upper, j plus equals 1. Right? Now you will fall off the edge in this case, right? But we want to fall off the edge because this is where it should be, where your bounds is done. Right? Okay, so now I've got my I and j. How do I return them? Can you do this, by the way, in Python? I don't think you can.
You delete the space.
Oh, what?
Delete the space.
Oh, well, I don't think that the space matters. I think it matters that
Yeah, you could.
you need to put it in a tuple, right? Oh, you don't? Oh, okay. It'll pack it. Is that what it's called? Okay. I'll trust you on that. And we'll find out for sure. Okay. Well, let's start testing this. Now here, I don't think you can you do this?
Yes.
Okay. I'll believe you. Print I. J. And I'll put in a comma here so that we can, see what it looks like. All right, let's see if this actually works. All right, 915, 915, 915, 915. Oh, that's why. Of course, I need to capture all those values now. I'm pretty sure that this works. But let's find out. All right, there's all our output. Do they match our expectations? 915, 015, 08, 00, 1919. I'm reasonably sure that this works and gives us what we want. Let me show you what you can do with it now. Right? So what we could do with it now is we could put it into a loop for, let's go with k. And in fact, what I'm going to do is I'm going to, let's do something, let's do this one right here. I'm going to go ahead and get rid of all this. For k in range of I to j, print array sub k. Now remember that we went from 2.5 to 8.5. It gives us all those numbers between those two ranges. Cool. What else can we do with it? Br is equal to of I, j. Print br. What does that give us? A subarray. Right? And I don't know if that's a deep copy or a shallow copy. Does anybody know?
Deep copy.
Is it a deep copy?
Shallow,
Oh.
because you specifically have to make it a shallow copy.
Array sub, yeah, let's go with 10
That's
is
the
equal
thing
to,
about this. It's definitely a deep copy.
Okay.
is it definitely a deep copy?
Yeah.
All right, so I'm going to change one of those, and we'll see if that changes for Burr. Okay, it is a deep copy, definitely.
Wow, that's the
Neat.
answer.
Cool? And all we had to do was implement a slight variation on binary search as a subroutine, use that, do 4 lines of code basically, and get an extremely powerful tool that will make your life way easier when you are searching for, or when you want to make these slices, right? If it's already sorted with respect to x, you've got your m minus delta, you've got your m. Just get that subarray. You've got your m plus delta. Just get your that subarray. There's your left and right slice. And it's a deep copy, so you're golden on that. Sort it with respect to y. And use the same tool, because now you've got y plus delta and y minus delta. Well, you should go y minus delta up to y delta, y plus delta, and now you've got the range in which to search, and you've got a simple for loop to do it.
Should it be like y plus delta plus 1? Or
Nope.
as long as you put
Nope,
y
not the way that we designed it.
Right.
Inclusive, exclusive.
Yes.
So it works with all the Pythonic code. If we did it, if we designed it that other way, then you'd be putting +1 on all your stuff instead.
Yeah, that'd be
Yeah, icky. Even by Python standards. Yeah.
What was y in that scenario?
Y is, so you've got a point in that main algorithm. Once you've got the left slice and the right slice, for each point in the left slice, you have to look at those 6 points in the right slice that might be closer, up to 6 points in the right slice that might be closer. So the x and y here, that gives you your point. And that's where the y comes from, here. It's that point, x and y.
So would x and m be the same for that?
X and m would not be the same, necessarily. In this, as depicted in this particular picture, yes. But x and y, it could be like a point in the middle of this slice right here, in which case you'd have a different x. M is computed once. Right? In fact, let's take a look at the pseudocode again here. Where is m computed? Yeah, let m be the x coordinate that splits the two partitions. So again, that's easy because if it's already sorted with respect to x coordinates, all you have to do is once you've split it, take the last point in the left partition, take the first point in the right partition, take their x coordinates, average them together, and that gives you your m. Right?
Forgot my question. Oh, would you have to check for things like directly above, or like,
You do have to check for things on those borders, which is why we designed this tool to be inclusive of on the ranges. Right? Everybody's familiar with this kind of mathematical syntax, right? If not, let's fire up the tablet.
yeah, it's inclusive.
All right. You know what? I never did it. Sorry. Quick time. There we go. There we go. So, sorry, I should have fired this up before. Let's get rid of this. If I write x, y, actually, that's a point. So if I write, say, 3, 4, that's on the number line, that's the interval from 3 to 4, inclusive. Right? If I write 1, 2 with a square bracket on one side and a parenthesis on the other side, this is again inclusive, but this is exclusive. We call this an open set because it refers to the number line, all the reals up to but not including 2. So they're an infinite number and you can get infinitesimally close to 2, but you never actually get there. That's depicted as 1 with a solid and then 2 with an open kind of thing here. Yeah.
Oh, I know what I was going to ask.
And you can do, yeah, you can do the other way like this.
Well, no, you just kept saying that, like, k, like the number of points in the range delta, like y plus delta to y minus delta.
Uh-huh.
Yeah, you said that that would be constant.
Yep.
But, like, it seems as though we just want to make a subarray and then just check for all the points in that subarray.
Then you will have n squared behavior. Because they could lie, all of the points on this right partition could lie within this slice right here. And now you're doing n divided by 2, n divided by 2 comparisons, and so now you're back to, yes, 1/4 n squared, but it's still going to be n squared.
So we're only checking for points at specific values.
Are within this range and this range because there are only 6 of them. Anything, if I've got this point here, x and y, anything above this region, this non-colored shaded region here, you know that that's more than delta away automatically. Don't even bother looking at
Oh,
those.
that's not what I meant by a subarray. I meant the subarray meaning like within that box.
This subarray could be empty, right?
Yeah, so that's
Just like we set up set up those empty slices as tests, 0, 0, and 15, 15. All right. I also did this. I did this the other day, and then over the last day when I was doing this write-up as an added bonus, I also wanted to learn about how Python does unit testing. And so here we go. If you want to learn how Python does unit testing, guess what? There's a unit test package. How many people have used that before? None? Okay. So here's what I learned. Right? You define a class. This is the simple way of using it. You define a class and you bring in unit testing, and you just run it as the main here. This unit testing framework will then look at this class and look at any method that begins with the word test, all lowercase. It doesn't have to have an underscore here. And then it will automatically run each one of those. Within that, you have to have some sort of an assertion of true, assertion of false, assertion of equal, or assertion of, close. If you've ever used, like, say, JUnit or CMACA or something like this, all unit testing frameworks are the same. They've got all these basic features. And then I was interested to see how this would work. I have a test list here. This is the same one that we were using before. And if you search for something outside the range, then you would expect 0, 0. You would assert that the actual that you get from that is equal to the expected. Here's another one. 2 to 7 would be 8 to 14. And how did I get 8 to 14? I wrote out the list, so I looked at the indices. Right? I tried to do a batch test. The drawback to this is this one is actually going to run 4 different tests. These are the inputs. These are the expected. And then I go through a for loop here to assert that they're all correct. All right? By the way, does anybody know what that syntax is? That's an explicit unpack. So take a look at inputs, say, of 0. It's a tuple, right? Well, bin search range requires lower, and upper. So I could, do something like inputs of I 0 and inputs of I j, or sorry, I 1, but so much typing, right? What can you do? An explicit unpack. It is not a pointer. Do not think of it as a pointer from C or something like that. Yeah.
How do you know that small kind of syntax, or where do you get it from?
I knew that you could do an explicit unpack, and so I just did a Google search on how to unpack a tuple for method arguments, and that came up immediately. Yeah, I mean, you get good at Google foo eventually, like knowing there's got to be a way to do this. This is how I would describe it, and then Google is usually good enough to come up with, well, here you go. Like just like I found out unit testing Python 3, and this package came up. Yeah.
You don't look up how to explicitly unpack.
No. Yeah, make sure that you put Python in there, otherwise you'll get some luggage company or something. Yes. Right. I also did it through a dictionary. Right. So here are some. Here's the inputs mapping to the outputs, input to expected, and it turns out that you can also unpack key pairs. Well, not key pairs, but this is input and expected. That's the key, and that's the value. And then I have to unpack the key, and I assert everything is equal. And then I can show you what it looks like when you, where am I here? Going to dev.
What package did you say that was?
Unit test. so what it says on the box. All right, Python 3, what did I call it? What did I call this file? Bin search test. There we go. And it results in, I don't particularly like the output because it's very, very terse as far as success goes. Now, when you see something that is unsuccessful, for example, suppose I'll just say I'll have a false positive here. This is what it looks like when it fails a test. Of course, it outputs that it should be 7, or it should be 7, but it was 0. Well, that's because I made it wrong. But that's what the output looks like. It says failed. It tells you how many failures there were. Otherwise, it just reports how many successful there were. It ran 4 tests, and they all passed because it's all okay. Now, again, remember that I'm actually running 2, 6, 9 tests. But because I'm doing it in one method, then it only counts as 1 test. And that's usual, too. That's what I would expect from, say, JUnit. And so that's why unit testing is perceived as kind of tedious, because if you want these to count as 9 tests, you have to do a lot of copy pasta. I usually look for a way around that so that it counts, so that this counts as 3 tests. I should be able to write it compactly like this, and I should be able to make it count for 3 tests. But I didn't find a way to do that in Python.
So when you all tests,
Yeah, you should. I mean, this is how I knew that my draft of this was correct, right? Before I did this, of course, I did what we were doing. I wrote out all these tests, and that's what made me annoyed that there's got to be a unit testing framework in Python. Fine, I'll just bite the bullet. I should learn it anyway to find out what it looks like. And it's easy to, just like learning one language and then learning another, for loops are all the same. Right? Unit testing frameworks are all the same. It looks exactly like JUnit. It looks exactly like CMocket. It looks exactly like any other unit testing framework. There are lots of bells and whistles that I didn't want to get into. You only do that when you have to, right? In an ad hoc manner. But I thought I would tell you, yeah, go ahead and go with unit testing here. Nice, right? Rather than, and by the way, when you do, somebody had asked about the size of their test cases for the all pairs, or the closest pair of points. Go to random.org, generate a bunch of random data. Write a script. I think we did that at the beginning when we did the brute force version of this. Write a script to generate 1 million random points. Then what you do is you go in and you make really, really, really close points. Or you make it, you make an input of 1,000. Then run the brute force algorithm on it so that you know what the answer is, right? And then run your algorithm, your divide and conquer on it so that you can check to see if that's the same answer. Or what you can do is you can take all these random points and then add 2 more points that are even closer. And you know that those are the 2 points that you're looking for, right? Put them somewhere in the middle so that you know that that one of them is on one side of the dividing line and one of them is on the other side of the dividing line, so that you're actually testing whether or not you're doing this properly, right? So you usually write test cases to try to break your code, right? And that's what you should do. Yeah.
But what if you have multiple pairs of points that are the same, shortest distance?
You only have to report one. Just make sure that this is the same distance as the web grader.
Okay,
Yep.
so should we record like the actual distance, like not only the 2?
I think the expected output should be the 2 points and the distance, yeah.
Oh,
Right.
cool.
But I don't remember on that. Okay. Well, we do have 1 minute left. I thought we would get more to it a little bit more, but in any case, let me ask you a very, very simple question, and then I'll give you some good news. So 7,387 times 4,562. Multiply those together for me.
Calculator, please.
That's the smart question, or the smart Alec question, right? Or the answer, I should say. Yeah, use a calculator. Right?
33699,494.
Okay, well, all right, that's a great answer of using a calculator, but you now live in a world where you don't have calculators. Go back to grade school. Do this.
Okay. 4 would be.
All right, good. 4. 2 times 7 is 14. 16.
Not
7.
16,
Not 16? Oh, 17. Thank you. We've already made a mistake. This is why we do use calculators. Let's see, 6.
Multiplication, not addition, so it wouldn't
Yep.
be-
Did I not do it right?
Well, it'd be like 9 times 6. Oh, no, you're right.
Okay. And then that's the first one, right? This is for multiplying 2 by this stuff. 6.
I thought it was
Yeah, 7, 8. Nope, multiplication. All right, keep going. Grade schoolers.
put a 0,
All right, put a 0.
place
And then 6 times
4.
7, 42. Carry the 4, 48, 2. So there's a 5 over there, 18, 3, 2. 6 times 7 is 42, so 44, right? Now, wait, before we go on, how many multiplications did I do at this stage? 4. Because 2 times 7, 2 times 8, 2 times 3, 2 times 7. How many did I do at this stage? Another 4. This is not a multiplication. This was just me writing 0, or in base 10, multiplication by 10 is just a shift. That's not multiplication. That's easy. And we're not going to do it, but how many here and how many here? 4 and 4. All right. In general, if you had an n-digit number, A, and an n-digit number, B, how many single-digit multiplications would you end up needing with this grade school method? N squared. Right? And this is why we use calculators, because as we know, n squared algorithms are unacceptable. Right? Can you do better? What's the theoretically best that you could ever hope for? Oh, so just n? Good, why?
Couldn't do it without looking at it.
Yeah, you have to at least look at the damn input, right? So, that's the theoretical best. Is there something in between? Right? Can we take this naive brute force approach, and can we use divide and conquer to get closer and closer and closer to this? Yes. We're going to look at one technique. We're not even going to hope to look at another technique called the fast Fourier transform. You might have heard of it before. But that fast Fourier transform can get it down to almost n log n single-digit multiplications. This is the theoretical best. I think that there's actually might be a lower bound of this too, just because of tournament-style lower bounds that are out there. But you can't hope to do better than linear. Right? Now the good news. Right? So we can stop this stream here. I think everybody is here.